Are you considering studying physics? What is physics? What kind of courses could you expect to take? What are the different subfields of physics? What type of careers might you expect to go into? All that and more in this video. Physics can, at base, be defined as the science of matter, motion, and energy. In the broadest sense, physics is concerned with all aspects of nature on both the macroscopic and submicroscopic levels. Its scope of study encompasses not only the behavior of objects under the action of given forces, but also the nature and origin of gravitational, electromagnetic, and nuclear force fields. Students who graduate in physics can generally expect to become an engineer, where they will apply all the principles of physics to design new technologies, or go into research and development, where they will do further study in the field of physics and help contribute to our human understanding of the physical universe. The study of physics includes a broad scope of topics ranging from optics, thermodynamics, nuclear physics, and quantum mechanics. There are many innovative technologies developed by companies which hire engineers who have core knowledge of all these subjects. If optics interests you, you could find yourself developing new technologies for optical fiber cables, which transmit data over long distances at high speeds and bandwidths, which provide several advantages over traditional communication technologies. Or you could work with data storage systems like compact discs or CDs, digital versatile discs or DVDs, and Blu-ray discs. All these storage systems include optical technology to read and write data to these disks. If nuclear physics interests you, you could find yourself working in a nuclear power plant. Nuclear energy is a significant source of low carbon electricity generation in today's modern world. Or you could work in the medicine industry to develop new medicines which require core knowledge of molecules and how can they be used to fight modern diseases. If quantum mechanics interests you, you could find yourself working in the medical industry developing new medical imaging technologies. An MRI scan uses the principles of quantum mechanics to produce detailed images of the body. Or you could work with GPS technology, which uses atomic clocks to determine your precise location on the Earth. A typical physics curriculum will include general physics, modern physics, mechanics, and quantum mechanics. Then, on top of that, you can take additional elective courses that are more tailored towards your concentration. First, you'll move on to your mechanics course. In this course, you'll learn about the basics of motion, kinematics, vector systems, and dynamics. In summation, this course is all about explaining how physical objects move. For example, if a car is driving along the street at a certain speed, how do we keep track of the position of the car as a function of time? Depending on the speed, which is the rate of change of position over time, and acceleration, which is the rate of change of speed over time, we can model the position of the car along the road as a function of time. In this course, you will learn about all the equations and techniques for mathematically modeling the motion of any physical object. You'll also learn about Newton's laws of motion and how to draw free body diagrams to predict the motion of a physical system being acted upon by external forces. The forces in a free body diagram could include gravity, normal force, friction, tension, spring force, and a lot more. Next, you'll move on to your optics course. Optics is the area of physics concerned with the properties and application of light. You will learn about the different models of light and how these models help explain some of the key properties concerning light. You will learn about diffraction, which is the ability of a light wave to spread out after passing through a small hole, and interference, which describes the behavior of light when multiple waves interact with one another, causing the combined light wave amplitude to increase or decrease. You will also learn about the ray model of light, which models light as a straight line along which light energy flows. You will learn about the laws of reflection and refraction, which describe how light rays bounce or reflect off a surface and how the trajectory of light changes when it passes from one medium to another. These laws help describe common everyday phenomena such as how we see ourselves in a mirror and how light bends when it passes through a glass of water. You will learn all the equations for describing how an image is formed through different lenses, such as a convex or concave lens, both of which deflect light rays differently. Next, you'll move on to your thermodynamics course. This is the branch of physics which deals with heat and other forms of energy. You'll learn about all the different thermodynamic terms, such as work, which is the transfer of energy in a mechanical interaction when forces push or pull, and heat, which is the transfer of energy in a thermal interaction when the system and its environment are at different temperatures. You'll learn about how heat is transferred in a system through conduction, convection, radiation, and evaporation. You'll also learn about heat engines, which is a device for transforming heat energy into useful work. A refrigerator can be thought of as the opposite of a heat engine. A refrigerator is any device in which external work is used to quote unquote pump energy from cold to hot. It transfers heat out of the system. You'll learn about the efficiency of an engine, which quantifies how good the engine is at transforming heat energy into work. Next, you'll move on to your nuclear physics course. This is the field of physics that studies atomic nuclei and their constituents and interactions. You'll learn about the structure of the nucleus, which contains protons, electrons, and neutrons, and the forces which hold the atomic nuclei together, namely the strong force, which is one of the four fundamental forces of nature. An unstable atomic nucleus is subject to losing energy via radioactive decay. Energy from an atomic nucleus can be lost from alpha, beta, or gamma decay, all three of which you will learn about in this course. You will learn how to quantify the half-life of an isotope, which is defined as the time taken for a substance to radioactively decay into half of its original mass. This is important information to know for scientists who deal with these unstable radioactive elements. Next, you'll move on to your relativity course. This course is primarily concerned with teaching you about Einstein's theories, which posit that time and space are relative, a concept which completely shook the scientific community at the beginning of the 20th century when Einstein published his theories. Einstein's two theories of relativity include special and general relativity. For special relativity, you'll learn how to use inertial reference frames, which can include any physical object that is either stationary or uniformly moving, to distinguish how time and space are altered at high speeds. In classical Newtonian physics, the principles of relativity are unobservable and hence irrelevant. However, when you have a moving frame of reference in which that frame of reference is traveling near the speed of light, time and space start to alter. You'll learn about both time dilation, which is the difference in elapsed time as measured by two clocks in separate reference frames because of a relative velocity between them, and length contraction, which is the phenomena that a moving object's length is measured to be shorter than the lengths as measured in the object's own rest frame. General relativity is an extension of special relativity to include all reference frames as opposed to just inertial reference frames, in which there is no acceleration in any reference frames. General relativity takes into account the effects of gravity on space and time. We know that massive objects in our universe have the effect of creating a gravitational force. In essence, general relativity posits that space-time is curved around these massive gravitational objects such as stars, black holes, and planets. This curved space-time affects how matter moves throughout the universe. The light from distant stars and galaxies essentially follows a curved path as it traverses near large celestial objects. So we may look into the night sky and observe a star to be at one place, when in reality it may actually not be where we see it. The light traveling from the star to the Earth could have taken a warped path, making it appear as in a place where it actually isn't. General relativity also helps explain many other astronomical phenomena that we observe. Then finally, you'll move on to your quantum mechanics course. One of the fundamental ideas in quantum mechanics is the wave-particle duality in light. Previously, light has been understood as a continuous wave of electromagnetic energy. However, our understanding of light shifted radically at the beginning of the 20th century when the scientific community adopted the photon model of light, which says that light consists of discrete particle-like units called photons. Previously, the energy of light was understood to be a continuous spectrum and increased indefinitely as the frequency of light increased. However, as light was now understood to be a collection of these discrete photon particles, each photon particle held a discrete amount of energy. Energy was not continuous, but discrete. This idea of wave-particle duality was extended further for other types of matter such as atoms, molecules, and electrons. Every particle of matter was understood to also behave as a wave which had some sort of wavelength. This led to physicists wanting to quantify the probability that any particle of matter will be in certain places at certain times. You will learn about Schrodinger's equation, which is used to calculate the probability that a particle is in any given place at any given time. Any particle of matter can be thought of as having a superposition, in which other words, being in multiple places at one time, that is until you measure it. You'll learn about all the theories and ideas behind superposition and the probability density function in this course. This covers all the core coursework you'll see in a typical physics curriculum. Once you have completed all your core coursework, you'll have the option of taking additional elective courses. Some of these options may include optics, quantum computing, particle physics, general relativity, polymer electronics, solid-state physics, and much more. I hope this video has helped you understand what you can expect to study while pursuing a degree in physics and the type of careers you can expect to go into. If you enjoyed this content, don't forget to comment, like, and subscribe. Thank you all for watching, and I will see you all in the next video.